And the next talk will be from Sakriani Sakti. She is an associate professor at Japan Advanced Institute of Science and Technology. Her research interest varies from like deep learning, graphical model frameworks, machine speech chain, zero source speech technology, multilingual speech recognition, and more. She gave us a pre-recorded video, so I will just play this video right now. Can everyone see my screen?
Yes.
Yeah, thank you. So I'll go ahead and play.
Hi, good morning, good afternoon, and good evening, everyone. I'm Sakriani Sakti from Japan Advanced Institute of Science and Technology. It is a great honor to be invited to this workshop, but I'm really sorry that I'm not able to present it directly due to certain condition. Okay, so today I will present self-adaptive machine speech chain in noisy environment. It may be different from the current widely used self-supervised learning, but I hope it provides an idea of how a machine shall have the capability to self-improve given the change of environment. And of course, this work was not done by me alone. It includes the contribution of several people, including Andros Chandra, Johannes Effendi, Sasi Novitasari, and Satoshi Nakamura. So we know that recently the trend in the machine learning community has adopted self-supervised approach to pre-trained deep networks. It refers to specific techniques that learn general representation given a large amount of unlabeled data. So here a portion of input is used as supervisory signal to predict the remaining portion of the input. After that, the learned representation can be utilized to improve performance on a downstream tasks, for example, speech recognition. And we all know several well-known self-supervised learning approaches that have successfully been applied for pre-training and improve the state of the spoken language processing. For example, CPC, APC, Walk2Fact, Walk2Fact2.0, QBERT, and W2VBERT. However, one of the main objectives of self-supervised learning is to make AI learn like a baby based on observation of its environment and interaction with people. Even in these workshops also state that baby learns their first language through listening, talking, and interacting with adults. And the question is, can AI achieve the same goal without much low-level supervision? So Benjo also in his keynote talk at NeurIPS 2019 also mentioned that we shall move the field of artificial intelligence beyond prediction and pattern matching and toward machine that think like human. So we need that system that can handle environment change and do continual learning, lifelong learning. So this talk will focus on this issue, which is a self-adaptive machine that can handle environment change. Okay, let's talk first about human language learning and communication. This figure was taken from an article that presents a study of baby learning and found that the fact of turning baby babble into language is because of the feedback loop process with the mother. The study by Lying also stated that for infants to start producing their first words, they must first begin matching the sound of babble and the sound of speech from the caregiver. So this is because they can listen and then after that they try to speak. Even when there is no parents or caregiver, the toddlers can continue learning how to talk by constantly repeating their articulation and listening to the sounds they produce. So this is one way for them to do self-supervised learning. So this is because they have a closed-loop speech chain, has a critical auditory feedback mechanism. So for children who lose their hearing, they don't have auditory feedback. So they don't have ability to listen what they say, and therefore it's difficult for them to produce the clear speech. Even adults who become deaf after becoming proficient with the language nonetheless suffer speech articulation decline as a result of the lack of auditory feedback. So another study by Hickok also found there is a sensory motor integration during speech processing. The auditory system is critically involved in the production of speech, and the motor system is critically involved in the perception of speech. So here he found that this SPT exhibits sensory motor response properties that activate during the perception and during also the speech articulation. He modeled an integrated state feedback control that have a communication between auditory and motor system. So the feedback loop mechanism is helpful for human, not only during training, but also during everyday communication. Because it plays an essential role in maintaining the fluidity of speech, and it allows the speech motor movement to be monitored and production error to be detected and corrected, which is the self-improve mechanism. So Dennis and Pinson in 1993 defined the speech chain in human-human communication as the process of speech transmission from the speaker to listener. First, the speaker will arrange his thought into linguistic form by selecting the right words. Then the words are articulated and produce acoustic waveform, which then travel through the air and received by the ear of listener. Finally, the hearing mechanism will be activated and recognize the message then sent to the brain. However, the speech waveform is not only received by the listener, but also by the speaker himself. So he can hear what he say, and this is because there is a critical auditory feedback. Okay, so let's talk about the machine speech chain. So we propose a closed loop speech chains model based on deep learning. The aim is to integrate human speech perception and production behavior. So if humans have the auditory feedback to listen their own voice like this, so we introduce also auditory feedback mechanism also to the machine. So the machine will have the capability not only to listen or to speak, but also listen while speaking. Okay, let me explain a little bit more detail. This is the standard approach where ASR is developed as listening component from speech to text, while TTS is developed as speaking component from text to speech. But despite the close relationship between speech perception and production, ASR and TTS research has progressed more or less independently without exerting much influence on each other. So here we introduce auditory feedback, the connection from TTS to ASR and from ASR to TTS. The mechanism allows training ASR and TTS with low-level supervision using unlabeled data. So here ASR and TTS can teach each other using unlabeled data and generate useful feedback. During inference, it is possible to use ASR and TTS model independently as the standard approach. So for example, when we receive speech data only, ASR will predict the transcription. As we don't know the ground truth of the transcription, we send to TTS to reconstruct the speech features. From here, we can calculate the loss between original speech and the predicted speech. And then we do propagation, backpropagation, and improve the TTS. So it is possible to improve TTS with the speech only by the support of ASR. On the other hand, when we receive only text data, TTS will generate speech features. As we don't know the ground truth of the speech, we ask ASR to listen to what TTS say and reconstruct the text. From here, we can calculate the loss between original text and the predicted text, do backpropagation, and improve the ASR. So it is possible to improve ASR with text only by the support of TTS. But current basic machine speech chain couldn't perform of unseen speaker. So to handle the voice characteristic from unknown speaker, we integrate a speaker recognition into the speech chain loop. It provides the possibility of TTS to handle the unseen speaker using one-shot speaker adaptation, like this. So similar to before, we can train with speech only or text only, but this time we will have speaker recognition within the loop. So given speech only data, ASR will predict the most probable transcription Y. Then speaker recognition provide a speaker embedding Z. Based on predicted Y and Z, TTS will try to reconstruct the speech. And then we calculate the loss and backpropagation. The same way, given the text only data, we sample a speaker vector Z from available speech. TTS then generate the speech features X given the embedding Z. Then ASR will listen what TTS say and reconstruct the text. And then we calculate the loss and do backpropagation. So this is the roadmap of machine speech chain. The left one is the VQVAE or vector quantized variational autoencoder. So this is the image of infant where this is really pure unsupervised learning and it still doesn't know what is the text transcription. So this is based on the codebook. So this is like a toddler version where this codebook version now is already become text transcription, and this will do continual learning not only during training but also during inference by listening while speaking. Okay, so now let's focus on the self-adaptive mechanism through listening while speaking. The standard TTS systems are commonly developed by assuming they are operating in ideal clean environment. So when the environment becomes noisy,
previously reported the entire agricultural concerns exceeding about $185 million.
As we can hear, TTS can perform well. Humans, on the other hand, can listen and be aware of surrounding sound and then speak louder in noisy place, which is called the Lombard effect.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
Of course, several works have addressed TTS in noisy situation. In the parametric model with HMM, the approach is to perform TTS post-processing and fine-tuning using Lombard speech data. In the neural network approach, one system performs transfer learning using Lombard speech data. Then another approach is by training multi-style TTS with Lombard or whisper speech, in which they will provide the desired speech style as an embedding. So although many works study Lombard TTS, most existing works only perform offline tuning with supervised learning. But we humans, we never fine-tuning ourselves before going to a party or noisy place. So how do you humans do? Again, this is because the human has speech change mechanism to speak while listening. So first we plan the speech and then speak. At the same time, we listen to our voice. Again, the auditory feedback play a critical role to plan the next speech. By doing this process continuously, we can adapt to the noisy situation by speaking louder. So humans change the way they speak dynamically given environment change based on auditory feedback. Unfortunately, most machines cannot adapt dynamically to the real situation. So here we propose machine speech chain inference for TTS in noisy condition. This is an advanced version of the basic machine speech chain. Here the feedback is utilized not only during training but also during inference. So to synthesize speech, we connect a TTS with modules that provide auditory feedback. The feedback here are SNR and the ASR loss that represent the TTS speech quality. We also apply a variance adapter in our TTS to predict the speech prosody. So by using this mechanism, TTS will speak louder with a high intelligibility in a noisy place. The basic structure in this work is transformer TTS based on tacotron structure. The input here is a character sequence and the output is the speech features. The right side is the proposed TTS architecture. So compared to the standard TTS, now we have not only speaker embedding, but also two additional auditory feedback, which are the SNR and the ASR loss embedding. Furthermore, we also have the variance adapter, which consists of three components: intensity predictor, pitch predictor, and duration predictor. Our variance adapter is applied to the encoder. So after we get the transformer output and the auditory feedback, all of them are combined into one and then sent to the variance adapter. On the variance adapter, its predictor will predict the speech prosodies, and the results are summed to the input as the final encoder output. For the experiment setting, we set up the experiment based on Wall Street Journal data. The Wall Street Journal data consists of clean multi-speaker English speech. We then simulate noisy speech by made noisy Wall Street Journal speech data, combining the original Wall Street Journal and the noise. The noise sounds here were white noise and the babble noise, and the SNR were SNR 0 and -10. The third data is natural Lombard speech. The natural Lombard speech was recorded by asking a single male speaker to read speech transcription in noisy condition. And then based on the natural Lombard speech recording data, we made a synthetic Lombard speech data set, which is the original Wall Street speech with the prosody modified into Lombard speech. We used the dataset mainly to train the proposed TTS. This table shows the architecture and the training data of the baseline TTS and the proposed TTS. All TTS systems here have the same encoder and decoder layer size, but they differ in the feedback component. Our baseline is the standard TTS and the TTS fine-tuning using Lombard speed with the supervised learning. For the TTS feedback generation, we also train ASR and SNR recognition model using the clean and noisy Wall Street Journal. And now let's see the result. In this experiment, we evaluated the TTS performance by speed intelligibility measure as ASR character error rate or CR. This is done by recognizing TTS speeds with noise. This table shows the result of the baseline system, the proposed system, and natural speeds at different levels of SNR. There are several baselines, the standard TTS and the TTS that perform fine-tuning with Lombard speeds. Here we also investigate three types of the proposed system with the SNR embedding only, with SNR ASR loss embedding, and the last one with SNR ASR loss embedding and variance adapter. And the best TTS system was the proposed TTS with SNR ASR loss embedding and variance adapter. It resulted in the lowest CR in noisy condition, outperforming the fine-tuned baseline. Now let's hear the speed segment in noisy condition. First is the claim speeds from the standard TTS.
And your terms previously reported the Italian agricultural concern.
And then the standard TTS in noisy situation. As we can see, we almost cannot hear the TTS speeds here. Now let's hear after the fine-tuning.
And your terms previously reported the Italian agricultural concern.
It performs better than the standard one. Now let's hear the proposed system. Starting from the first one, using only the SNR embedding.
The terms previously reported the Italian agricultural concern.
And then SNR and ASR loss embedding.
And your terms previously reported the Italian agricultural concern. About $195 million subordinated debt as part of the transaction.
And the last one with SNR, ASR loss embedding and variance adapter.
Under terms previously reported the Italian agricultural concern.
And this is natural Lombard speeds.
Under terms previously reported, the Italian agricultural concern.
So we have seen that the best proposed system successfully adapted to the situation dynamically. This graph shows the TTS speech intelligibility with various embedding coefficients. This experiment was done by applying a coefficient to SNR embedding and ASR loss embedding in encoder output and decoder input. The default coefficient was 1 for both embedding. In the clean condition, the best performance was achieved when the ASR coefficient 1 and SNR coefficient 0. So in this condition, the TTS only utilized the ASR. But in noisy environment, the best performance was achieved when both ASR and SNR coefficient was equal to 1. So this experiment shows us that SNR and ASR feedback are equally necessary. Next, let's see how the feedback loop affects the TTS speeds. So as we see before, the proposed TTS synthesized the speeds in several feedback loops. The effect of feedback iteration number can be seen in the graph. As we can see, the higher loop iteration resulted a better performance in noisy condition. This experiment result implies that the proposed TTS performed dynamic adaptation in several loops, listen to its voice and the noisy environment, and then speak louder. Okay, so here we already showed the machine speech chain, which inspired by the human speech. We propose a machine speech chain to achieve low-level supervision. It enables ASR and TTS to assist each other when they receive and pair data. And in the multi-speaker machine speech chain, it improved machine speech chain to handle voice characteristic from unknown speaker, where TTS can generate speech with similar voice characteristic only with one spot speaker examples. And the last one, finally, we showed that there is a possibility to self-adaptive machine speech chain that use the TTS with auditory feedback. It can improve the TTS speech intelligibility in noisy condition. So this dynamic adaptation with auditory feedbacks is critical not only for human, but also speech generation to do self-improvement. Okay, this is the overall publication of machine speech chain. And this is the citation of this presentation. Thank you.